Welcome! This video is part of a series on the xv6 operating system kernel. In the previous three videos, I gave a brief introduction to the RISC-V architecture, more or less independent of xv6. I covered all you need to know in order to understand the xv6 kernel without going into great detail on the aspects that you can safely ignore. In this video, I'll cover the initialization that happens when the kernel begins execution. I'll cover everything that must happen in machine mode before we jump to the main function and switch into supervisor mode. I'll go over these three files. Execution begins with a few instructions that must be in assembly code, and this comes from a very short file named entry.s. Then the kernel executes some C code in machine mode, and that's from the file start.c. Start.c ends by jumping to the main function. The file risc5.h, or riscv.h, contains a bunch of small helper functions. This is going to be a fairly long video, so I want to begin with a brief overview of the entire startup procedure, everything that must happen in machine mode before we can take the jump to the main function. All cores share the same memory, but each core needs its own stack. As you know, C code depends on there being a valid stack. So somewhere there's a big region of bytes, and each core will get a small chunk of this region to use for its stack. There are 8 chunks, one for each core. To be precise, there's a 32 kilobyte array that is divided into 8 chunks, so each core gets 4 kilobytes for its stack. Execution begins with some assembly code at location _entry. This short bit of code looks to see what core it's running on and initializes this core's stack pointer register to point to its private stack area. After this, it jumps to a function called start. The start function is written in C and does all the initialization that must be done in machine mode. We don't have any page tables yet, so it clears the SATP register to prevent address translation from happening until the kernel is ready for it. Then start initializes the MIDELEG, MEDELEG, and SIE registers. This will cause all exceptions and interrupts to be handled by trap handlers that run in supervisor mode. There's something called the physical memory protection scheme, but it's not used in xv6. Start will initialize a couple of registers to effectively turn off the PMP system, so you can ignore it henceforth. There are a couple of registers that are initialized to cause all timer interrupts, to cause supervisor mode interrupts instead of machine mode interrupts. The time of the next timer interrupt is controlled by a register called sTimeCompare. Each core will have an interrupt every 1/10 of a second. After each timer interrupt, this sTimeCompare register will be incremented by 1/10 of a second to schedule the next timer interrupt. The start code will initialize the sTimeCompare register to schedule the first timer interrupt to get things going. The delay of 1/10 of a second will be enough time for the kernel to initialize everything and be ready to deal with that first interrupt when it happens. The start code will also move the number of the core into the TP register, the thread pointer register. Since the kernel, which is running in supervisor mode, can't access the mHeartID register, it'll need another way to learn what core it's running on. There's a function called CPUID, which is called all over the kernel, and it just returns the value saved in the TP register. Finally, start sets up for and then executes the mret instruction. This will simultaneously switch into supervisor mode and make the jump to the main function. Main will never return and will stay in supervisor mode with user programs running in user mode, but never again returning to machine mode. In order to access the various control and status registers, Specific assembly instructions, like CSR read and CSR write, must be executed. Each of the instructions we're ever going to need is encapsulated in its own tiny function with names that begin with R underscore for reading a control and status register and W underscore for writing a control and status register. All these little functions are in a file called risc5.h, which gets included in any .c file that needs it. This .h file also has several predefined constants and preprocessor macro functions that will come in handy later in various places in the kernel. For example, page size, which is 4 kilobytes, and page round up and page round down, which round addresses up and down to the nearest 4 kilobyte page aligned boundary, and max VA, which is the size of all virtual address spaces, or equivalently the address of the byte just beyond the address space. There are also some useful definitions for working with page table entries, which have a specific bit field layout. So that's what the remainder of this video will cover. Okay, with that overview, let's now get into the details. The kernel will be running on a number of cores, and each core will need to have its own stack area. So the first thing that must happen is the stack pointer, that's the SP register, must be initialized properly to something different for each core. We'll give each core a stack of 4 kilobytes like this. Since stacks grow downward on RISC-V, we need to initialize SP to the top of the stack area that's to be used for the core. We can support up to 8 cores, so we'll need 8 times 4 kilobytes for all of these stacks. This space is pre-allocated in the file start.c with a variable named stack0 right here. NCPU is a predefined constant giving the maximum number of cores, which happens to be 8. So it's a byte array of the right size. With RISC-V programming conventions, the stack pointer must always be quad word aligned, that is, evenly divisible by 16 bytes. This underscore, underscore, attribute, underscore, underscore stuff is some special syntax directing the C compiler to align this array on a 16-byte boundary. With a type of character, the compiler would normally not bother to align it. This array is defined outside any function, so it'll be visible in separately compiled files. So now let's look at the file entry.s. When we link the kernel, we'll instruct the linker using the file linker.ld to place this particular chunk of code at location hex 80000000, which is where execution will begin on power up. So this instruction is the first instruction that the core executes. The .section is an assembler directive to place everything that follows into a text section, which is what we use for memory that contains executable instructions. The first instruction is labeled underscore entry, and the .global directive will make this name available outside this file. Other labels, like spin down here, will by default be local. This code is running simultaneously on each of the 8 cores. It's okay if we have fewer cores than 8, but 8 is the maximum number we can accommodate without updating the NCPU constant and recompiling. Each core has a number called its heart ID, and this code takes that number, multiplies it by 4 kilobytes, and adds it to the starting address of stack 0, and then stores it in the SP register. As I mentioned, stacks grow downward, so we actually want the stack to begin just beyond its 4K region, that is, at the very beginning of the following 4K block. And that's why we first add 1 to the core number before multiplying. This is a load address instruction, which moves the address of the stack 0 array into SP. Then we have a load immediate, which moves 4K into register A0. This multiplication is done by the assembler, not at runtime, but you could have just written 4096 instead. The CSR read instruction copies the core number from the control and status register named mHeartID into register A1. Then we add 1 to it, and then we multiply A0 by A1, that is by the 4096 in A0, and place the result in A0. And then we add it to SP, and we're done. Finally, we use a call instruction to transfer to the function named start. Start will never return, so we could also have used a jump instruction. But if for some reason start should ever return, we'd fall through to this infinite loop, which repeatedly jumps to spin, which would lock up the core. Before we look at start.c, let's look at the file risc5.h. This file contains a bunch of helper functions that allow us to use assembly code from C files. Let's take a look at this first function, rmHeartID, which is used to get and return the number of the core this code is running on, which is in the control and status register named mHeartID. So it returns a 64-bit value. There's a local variable named x, which is returned from this function. The ASM volatile statement is a directive to the C compiler to generate an assembly instruction. In this case, it's the CSR read instruction. The compiler will insert whatever is within these quotes, which is the CSR read instruction with its operands, directly into the program. The first operand, that's the destination register, is given symbolically, and the specific register to use will be chosen by the compiler. This other stuff tells the compiler to use whatever register it's already using for the variable x, and that the instruction will modify the register. The function then returns x, which is the value we want. This function is specified as inline, so the body of the function, which is basically just a single CSR read instruction, will be inserted directly wherever the function is invoked. This eliminates the need for any call and return instructions, and for short functions like this, it makes the code smaller and faster. This is a .h file, which will be included in lots of .c files. This function has been tagged as static, which makes its definition local and private to whatever .c file it was used by. Without the static keyword, the linker would see lots of definitions of this function, once for every .c file that included it, and the linker would complain. Now, this .h file is included in many .c files, but it also contains some constant definitions down at the bottom that are needed in one of the assembly code files, so it's also included in a .s file. We want that .s file to see only those constant definitions. These C functions here would really confuse the assembler, so we need to hide them, and that's the purpose of this # if not defined directive. Whenever the preprocessor is used by the assembler, this symbol, ___ assembler ___ will be automatically defined. This if is matched down here, and when used in a .s file, only these definitions would be visible. Okay, there are a bunch of very similar functions in this file. The functions whose names begin with r_ will read and return a control and status register. For example, here's one that returns the M status register, and there are a bunch more. One for each control and status register whose value the C code will need to obtain. There are also a bunch of functions to update CSRs, and the names of these all begin with W underscore. For example, the function W underscore mStatus is passed a 64-bit value, and it uses the CSR write instruction to store that value into the mStatus register. Here's one to update the MEPC register. I'm not going to go over all of these functions. Just know that whenever you see a use of a function whose name begins with R underscore or with W underscore, there is one of these short inline functions being used. Notice that we've also got these definitions related to the mStatus register, which we will be using later in this video. Recall that there's a 2-bit field called MPP, the previous privilege field. The first definition defines where the MPP field is within mStatus. There are different values that can go into this field: binary 11 and 01 and 00, which are given by the next 3 definitions. We've got similar definitions for the sStatus register for the bits named SPP, SPIE, and SIE. In my quick summary of the RISC-V, I didn't mention the UPI and UIE fields, since these are not ever used in xv6. In fact, their definitions are included here, but they're never used in xv6. If they're still in the code by the time you watch this video, then just ignore them. We've also got a few other definitions of bit fields sprinkled in amongst the read and write functions. Also, let's look at this function, make SATP. In my summary video, I sort of suggested that the SATP register contained the address of the root node of the page table tree. Actually, it also has a field to specify which page table scheme to use, and it doesn't contain the entire address of the root, just the page number. So the function make SATP will transform a full address into this proper form. This is a preprocessor macro function, so it gets copied in line wherever it is used. I also want to mention the interrupts on function, which will set the interrupts enabled bit, that's SIE, in the sStatus register. You can see it first gets the sStatus register, then forces the SIE bit to 1, and then writes it back to the register. This function will be called by the kernel to enable interrupts. There is also an interrupts off function, which will clear the SIE bit. The kernel will use this function whenever it wants to disable interrupts. Finally, we have a function to get the value of the SIE bit. So from time to time, the kernel will perform some internal consistency checking to make sure that interrupts are disabled when they should be. This function retrieves the SIE bit and returns it, or more precisely, it returns true if and only if interrupts are enabled. Also, here we see the function xv6_VMA, which I mentioned in another video. It just executes the xv6.vma instruction. The kernel will use this to flush all entries from the TLB cache from the translation look-aside buffers. Okay, now we've got some handy definitions. Pages are always 4 kilobytes in size, so that is page size. The offset into the page is 12 bits, which I discussed when I described page tables, and that's page shift. Then we have functions to round an address up to the next multiple of 4 kilobytes, that's page round up, and to round down to the next page boundary, which is page round down. The next 5 definitions define exactly where in the page table entry we can find the various protection flags. That is, the valid bit, the readable, writable, and executable bits, and the user bit. Remember that the page table entries in the index nodes don't contain actual addresses, Since all pages are aligned, they only need to store 44-bit page numbers. The function physical address to page table entry is used to convert a physical page address into a page number and position it for insertion into a page table entry. And the function page table entry to physical address is used to extract a page number from a page table entry and convert it into an address. PTE flags extracts the 5 bits that are the protection flags and some other flag bits, which in xv6 will always be zeros. Recall that each virtual address contains a page number which can be decomposed into 3 fields of 9 bits each. These functions are used to deal with those fields. Finally, here we have max VA, the size of every virtual address space. This is the maximum virtual address, or actually the address just beyond that. Recall that with the SV39 scheme, virtual addresses are 39 bits. With RISC-V, they are, but xv6 only uses 38 bits. And note that 9 plus 9 plus 9 plus 12 minus 1 is 38 bits. So with xv6, all virtual address spaces are actually only 1/4 of a terabyte in size and not 1/2 of a terabyte. The comment makes some cryptic remark about problems with sign extension. I'm actually a little curious about that, and I might look into that a bit later. Okay, now we're ready to look at the file named start.c. It contains only 2 functions, the start function and a function to initialize the timer, and these are pretty short functions. Here again is the area that will be used for the 8 stacks. Remember that each core will begin executing this code in machine mode concurrently. And after seeing the code at entry, we know that the stack pointer will have been initialized before start is called. If we have fewer than 8 cores, it's no problem. It's just like the missing cores are really slow, infinitely slow. If they ever start back up or they get added to the system after the kernel has been running for a while, then it's no problem. It's effectively the same as if they were just running very slowly. Of course, core 0 is necessary, and nothing can happen until core 0 says that the initialization is complete and allows the other cores to proceed. The start function will end with an mret instruction. As I described in the last video, this is used to jump to the main function while simultaneously switching into supervisor mode. We do this by presetting the previous privilege level field, the MPP field in mStatus, to supervisor mode and setting the previous program counter, that is the MEPC register, to the address of the main function. First we get mStatus, then we zero out the MPP field, then we set it to the value for supervisor mode, and then we write it back. Next we set MEPC to the address of the main function. So we're now ready for the mret instruction. But first we have some other stuff to do. We zero out SATP. If SATP has random garbage in it on power up, this could cause havoc the moment we got into supervisor mode, since paging would automatically be turned on with a random page table. That's not good. So we set SATP to 0 here to prevent that until SATP is initialized with a proper page table. Then we delegate all exceptions to supervisor mode by setting the MEDELEG register to all ones. Well, at least we set all the bits which are defined, if not all the full 64 bits. And we delegate all interrupts to supervisor mode by setting the MIDELEG register to all ones. And again, we don't care about the upper bits which are not used. Now, any exception or interrupt that occurs will be handled in supervisor mode using the S registers and not in machine mode. We also set a couple of bits in the SIE register, That's lowercase SIE, not to be confused with the uppercase SIE bit in the S status register. Supervisor code could, if it wanted, selectively enable or disable various interrupt types. But since xv6 won't be doing this, we'll set these bits to enable the two interrupt sources we care about. SEIE is external interrupts enable. That will be the disk and keyboard. And STIE is timer interrupts enable. Briefly, I mentioned the PMP, or Physical Memory Protection Scheme. This system is not needed or used by xv6. I'm not going to go into detail about this system. I covered it in another video in much greater detail. Let me just say that we want to mark all physical addresses as readable, writable, and executable as far as the Physical Memory Protection Scheme goes. By initializing the first two PMP registers like this, we're creating one huge region covering all addresses and marking it readable, writable, and executable. After that, the PMP system will never complain or cause address exceptions. Next, we initialize the timer. This is done by 4 instructions that are pulled out into a separate function called timer init, which is here. So we call timer init, do these 4 instructions, and return. Frankly, I think it would have been clearer to move all these 4 instructions directly into the start function and eliminate timer init altogether. They do it this way as a historical artifact of a really ugly hack that was previously necessary, but which has since been fixed. Maybe this code will be moved into start by the time you see this video. The first thing we do is set the STIE bit in the MIE register. This is now unnecessary and it does nothing since interrupts have already been delegated to supervisor mode. Enabling timer interrupts in machine mode is now pointless, and hopefully someday this line will also be gone. The RISC-V spec describes an optional extension called SSTC. This extension will allow timer interrupts to be seen by supervisor code. xv6 makes use of this extension, and I think the previous hack was required because QEMU didn't originally support this SSTC extension. Well, anyway, we set a bit in the M environment configuration register to enable this timer interrupt extension to work. Then we enable a bit to allow supervisor code to use the timer interrupt mechanism. The way timer interrupts work is this. There are 2 registers, time and time compare. Time tells the current time. Time is measured in ticks of some global clock. In the previous video, I said that time was counting cycles. That was somewhere between a simplification and just plain wrong. In fact, there's a global oscillator generating ticks at a regular frequency. There is only one counter, so all references to the time register from all cores will return the current time value of this counter. Within QEMU, this counter is advancing at a frequency of 10 MHz by default, while each of the cores has its own internal cycle oscillator which regulates instruction sequencing and will be running at different speeds. While the tick counter, which is time, is shared, each core has its own time compare register. This is the time at which the next timer interrupt should be generated on that core. When the time counter finally reaches the value stored in time compare, a timer interrupt will be generated on that core. So here we initialize the time compare register for this core so that we'll get a timer interrupt in 1 million ticks. This will be the first timer interrupt. And we need to initialize this before we go into supervisor mode, or else we might get a spurious timer interrupt too soon before everything is properly initialized and the interrupt can be properly handled. Later, we'll see that after each timer interrupt, the core will increment the time compare register by another 1 million. So with a clock frequency of 10 megahertz, this means that we're getting 10 time slices per second. That is, each time slice is coming after 100 milliseconds. For a system with only 10 or 20 processes and 8 cores, that's going to give pretty good responsiveness. With 8 cores and, say, 10 time slices a second, that's 80 time slices per second. So each of the, let's say, 10 processes would get about 8 time slices per second, which is every 1/8 of a second. Now this is just a quick ballpark estimate since there's overhead and randomness as well, but it's good enough to give you an idea. Anyway, then after this we return to the start function. Here we grab the number of the core we're running on and we save it in the TP register, the thread pointer register. We do this because supervisor code can't access the mHeart ID register. So instead, the kernel often invokes a function named CPU ID. Here it is. This function just returns the value of the thread pointer register. The CPU ID function is used throughout xv6 to return the number of the core that the code is running on. And finally, we execute the mret instruction. This causes a jump to the address in MEPC, which is the beginning of the main function, and simultaneously, mret will switch the core into supervisor mode. Okay, this is a great place to stop. Before I go, can I ask that you please share this video with any classmates you might have who are learning about xv6? And then let me end by saying thanks for watching, and I'll see you in the next video.